So we're looking at media independence of the IP protocol, and I was talking about IP allowing a mixed environment where different layer one protocols technologies can coexist, right? IP does not care if the underlying network is Ethernet, Wi-Fi, frame relay, does not care. If the physical medium is copper, fiber, wireless, it does not care. Why is this important? One, it allows coexistence, the obvious one. Two, it also allows, let's say you want to adopt new technologies at the physical layer. If we have a new technology at the physical layer, it doesn't necessarily mean you have to change everything to the layers going up. Why? Because as you go from layer one to up to layer three, this layer does not care what is happening down there. So therefore, you won't need to make any changes to the layers up there. Basically, that's what it means. And when we talk of advantages of the layered model, changes in one layer don't necessarily affect changes in the other layer. That's why we have a layered model. Very important. I think everything from the benefits of the layered model to what we are talking about here, it basically aligns because changes that we can make at this layer or even at this layer, it won't affect layer number 3. Changes that are happening at layer number 4 going up, they will not affect layer number 3. So it just depends on the type of encapsulation you have, depending on the data you have. If data from the upper layers is X, we encapsulate it accordingly. If it is Y, it is encapsulated accordingly. Then the information that we get here can be translated to the layers below, regardless of if it was X at this point, if it was Y in layer number 4. It does not care. So that's where the media independence comes from. I think it also touches on layer number 2. Layer number 2 also do not care what is happening in the upper layers. It just translates whatever is coming from the upper layers so that that language which is being spoke from the upper layers can be understood in the lower layers. That is the role of the data link layer. So I think it works hand in hand to satisfy this media independence. Layer number 2 also works hand in hand with some layer 3 protocols so that we have media independence. Irrespective of whatever media that we have, we can still communicate. So I was talking of an example here. You can see here we have copper Ethernet between the PC and the router. Then we have a serial link between those two routers. The information, the packet that we are sending here, it's still the same packet, but it does not care. Here we have Ethernet, here we have serial. It is still the same packet. What changes might just be the header information a little bit, but it's still the same packet. So those are some of the characteristics that we have of the IP. Let's move. The network layer will establish the MTU, maximum transmission unit. Network layer receives this from the control information sent by the data link layer. The network then establishes the MTU size. Fragmentation is when layer 3 splits the IPv4 packet into smaller units. Fragmenting causes latency. IPv6 does not fragment packets. A router goes from Ethernet to a slow one with a smaller MTU. That's an example. Okay, let's start by defining what the maximum transmission unit is, the MTU. The MTU is the maximum size of a packet, of a data packet that can be transmitted over a medium, the maximum size of a packet. So at layer 3, when I say packet, I'm talking of data in layer 3. When I say segment, layer 4. When I say data 567, when I say frame 2, that's very important. So the MTU defines the maximum size of a packet that can be transmitted. Why is it important? It's important because it determines the size that is supported by the medium. Right. The size that is able to be transmitted by Ethernet. Let's say Ethernet is able to transmit size 7. It's different from the size that is able to be transmitted by a serial link, for example. A serial link might transmit size 5. It's different. So what happens is the data link layer, it sends some information to the network layer. So from layer 2 to layer 3, information is sent that the medium that we are using at layer 1 is Ethernet. And the frame that can be processed by the layer 1 medium that we have, which is Ethernet, is of size, to be more specific, I think for Ethernet, it should be 1.5. Is of size 1.5. So the packet that you are going to prepare at layer 3 should correspond and should be less than 1.5. Because if it is more than 1.5, it will not be able to be processed by the medium. So that's why the MTU size is very important. The size of the packet is important because it determines the size of the frame, which determines the size of information that the medium will be able to transmit. And if it is huge, larger than the size which is required, then that's a problem. In chapter number 3, module 3, we talked of message size being important, right? And we talked of segmentation at layer 4. That's where it starts. At layer number 3, we also have something that behaves like segmentation, where if a report from layer 2 comes that our size is size 5, and if the packet receives a size 7, it will need to fragment that size 7. So if we fragment that, maybe we might get some packets, 2 packets, 3.5, 3.5. Then these are sent to the to data framing. Then they can be easily transmitted because they are of a size that is below the size that can be allowed by the medium. I hope you're getting it. I hope I'm getting my point across because this is very important. So just to summarize, layer 3 determines the MTU size. It determines that based on information that it gets from the layer 2. The layer 2 has information about the maximum size that can be supported by the physical medium. So from the maximum size that can be supported by the medium, a message is sent to the layer 3, then that determines the MTU size. The MTU size examples for Ethernet, I just gave you is 1.5, the most common ones. Then we have triple P over Ethernet. It's 1.4, 1.492. I only know of those two. So for Ethernet, it's 1.5 MTU. Right. So the example we're being given here, if a router is taking information that goes from Ethernet to a slow one with a smaller MTU. Let's take, for example, Ethernet 1.5 going to triple P over Ethernet, which is a smaller MTU. What will happen to this MTU, which is a larger size? It will need to be fragmented. And fragmentation is when layer 3 splits the IPv4 packet into smaller units. Why? So that we can have at least At maximum, I think good English, at maximum, this size. Right. Fragmentation causes latency. Why? If you fragment, let's start with segmentation. If you segment, if you break down a message at layer 4, that is segmentation. You need to sequence. You need to sequence those segments, number them. This is packet number, this is segment number 1, this is 2, this is number 5, this is 4, this is 3. So that when it gets to the destination, they can all be sequenced. 1, 2, 3, 4, put in order. So that we can easily interpret the message that is being sent. When we talk of that numbering, when we talk of sequencing, it means more overhead. There needs to be information in the headers that says this segment is segment number 1. That information means more overhead. More overhead means more information to process when we get to a device like a router. More information to process, more time, latency. Latency is a problem in a network. One of the goals to have for a very good network is latency. Very small. Latency should be very, very small. Right. So fragmenting causes latency, and that is where it comes from. IPv6 does not fragment packets. That's an advantage of IPv6. It does not segment. If it does not segment, IPv6, what it basically does, instead of with IPv4, layer 3 sends a message, layer 2 sends a message to layer 3. That the size we are supposed to have is this size. And if the size from above here is bigger than this size from below, then we fragment. We break down the information so that it is at max the size that is being provided from layer 2. However, with IPv6 sends information if this one is larger than the MTU, is larger than the frame that is required at this point. Actually, with IPv6, a frame is allowed to get here. And if it is larger than what is necessary, a message is sent back. Your MTU is too huge. You need to reduce the size. Then the message is sent all the way to the host. You need to reduce the size. So size is reduced from there. There is no fragmentation at this point. With IPv4, the layer 3 performs segmentation. With IPv6, the message is sent back to the host. You need to reduce your size. So that's the difference between those two. No fragmentation with IPv6. Fragmentation with IPv4. Very important. It might sound silly until you get a question. Why is there no fragmentation in IPv4, in IPv6? Simple questions like those. All right, let's get to the header. The version 4 IP is the primary communication protocol for the network layer. The network header has many purposes. It ensures that the packet is sent in the correct direction. How does it ensure that? Routing. It contains information for network layer processing in various fields. We're going to look at those fields. The information in the header is used by all layer 3 devices to handle the packet. The most important information in the layer 3 header, the IP addresses, the source and the destination mark. Let's quickly look at the packet header fields. When we looked at the data link layer, we looked at the frame header fields as well. Starting with SFT, source destination mark, our payload, error check at some point, a couple of more elements that are missing, but those were the fields for the frame. With the Packet header, we also have the same thing. It is in binary. It contains several fields of information. Diagram is read from the left to the right, 4 bytes, 32 bits. So it is 32 bits. You read from this side, going this side, then from the top to the bottom. That's how you read that diagram. This is just an abstract, by the way. This is not how the information is actually being transmitted. This is just an abstract. A visual image of what a packet looks like. Right. The two most important fields are the source and destination IP. Very important. Protocols may have one or more functions. Okay, that's basic. That's basics. Nothing much here. Let's go to where the header fields are explained in the next slide. Right. So header fields, we have the version. The version basically indicates the IP version. If it's IPv4, then the version is this one. If we have IPv4, the version is version 4. So we can either have version 4 or version 6. Right. Differentiated services, it's a field which is used for QoS, quality of service. When we talk of quality of service, we talk of traffic prioritization, traffic priority. So basically, in simple terms, it's a label where we label traffic. So if we have traffic A and we label it 100, and we have traffic B and we label it 90. If the number which is highest is our priority, it means every time traffic A and traffic B are being transmitted at the same time, this will always be preferred over this one. But how do we know which traffic to prefer? It's because of that number that is there. So QoS is basically, in simple terms, a label that we can put on traffic so that when we wanted to prioritize, we look at that label and we say, this is a higher label, if I can say, therefore it needs to be prioritized. So this differentiated service explains that kind of a label there, which is used for quality of service. Then we have the header checksum, which is used to detect corrupt IPv4 headers. We have the TTL, a layer 3 hop count. When it becomes 0, the router will discard the packet. This one, TTL, very important. A lot of questions will come on this one. TTL, it is used to prevent loops. Loops in a layer 3 network. When you talk of loops, so let's say we have a network, router. All right, we have a packet from PC1. We want to send our packet to PC2, but Toisa IP address is serial by destination mark, which does not exist in all the networks that are up. What will happen to that packet? Packet partnership up. Forward maybe to the network of last resort or the default route. Maybe default route yaro inoshita up. Forward yoshita up. Packet rinoramba richitenderera up. Because harina a destination network yataurwa iri correct or iri consistent to my networks aripa. That packet without TTL rinoramba richitenderera kudai richingori processor. That is a loop. What it means, when it is getting processed up, we are processing information which you don't need. Processing power router is being wasted. Congestion, latency, performance goes down because of this loop. So imagine if we have a lot of packets that are like this. One packet, you might not see the effect, but a million packets circulating because they don't have a destination network, that's a problem. That's why we have TTL. What TTL does, It has a number. So if that number, for example, is 10, if that number is 10, it means when a packet goes from this router to this, that number is reduced by 1. We have 9, 8, 7, 6, 5, 4, 3, 2, 1. When it gets to 0, the packet is dropped. It can no longer continue being in the loop. So the TTL is just a number which, when you go from one router to another, that number is reduced by one level. And when it gets to 0, the packet is dropped automatically. That's the TTL. The protocol ID is the next level protocol. What is the next level protocol? Especially the layer 4 protocol. The next level protocol, we have TCP and UDP. We'll look at those a lot. What is the next level protocol? Of which the next layer, we can talk of the transport layer. The source and destination MAC, that's not an issue. 32-bit source address, 32-bit destination address. We have a couple of fields that we're missing here. Let's go back here. The ID, we have the ID. We did the ID. No, we did not do the ID. So this one is missing. Okay. All right, so this one is missing. This one is missing. This one is missing. The total length is missing. Header checksum, we did that. Protocol, I think we did that as well. Right, the identification. This is used for fragmentation. I think this whole layer here is used for fragmentation, this one. All right, so tighter fragmentation here, the fragments needs to be identified. Put my numbers on them so that you can identify this is the first or this is the last segment. And the identification, this flag, and the offset is responsible for that. So this layer is responsible for the fragmentation of an IPv4 packet. The total length, that's the total length of the whole packet, if I can say, the header plus the data that we have. Then we have the header length, internet header length. This is just the header, the length of the header. Just the length of the header. What else did we miss? I think that's it. The protocol. Okay, ID is the next level protocol. We've done that. So I think that sums up every header field that we have. Very important to understand these fields because you definitely get typical questions. You're just given an explanation of something and they relate that explanation to the field. What does that describe? And you have to identify the field with the basic description of what the question gives. Right, going to version 6 packets. Version 4 has 3 major limits. 1, address depletion. 2, lack of end-to-end connectivity. 3, increased network complexity. When we talk of address depletion, we have basically run out of IPv4 address. Right. In this era, series is IoT, Internet of Things. Internet of Things means almost everything has an IP address. Has my IP addresses, probably my computers, my routers, my switch, with the devices, the name IP address, my server, right? But in today, we have billions of addresses that are needed because of IoT. A fridge now has an IP address. Maybe not, definitely not mine, but with IoT, it means everything in your home will need an IP address. Smart homes, your fridges will need an IP address. Your cameras will need an IP address. everything that you need to monitor. Your cars will have an IP address. Those cars that you have to drive by themselves, they'll need an IP address. So it means we are running out of IP addresses because of IoT. Uh, how many addresses do we have, by the way? It should be 2 to the power of, let's say 2 to the power of 16. What's that? It should be that. That's the number of addresses that we have IPv4. If I remember well, let me use my calculator. 2 to the power of 16. No, they're more than this. Let's 2 to the power of 24. Close. 2 to the power of 23. No, close. How many IPv4 addresses do we have? Just a minute. Can someone Google how many IPv4 addresses we have? I think it's millions. It should be 18 million. How many IPv4 addresses are there? No, it's not 18 million. It's 2 to the power of, why am I using 16? Yeah. It's 2 to the power of 32. How many addresses are these? 4, 4, 294, 967, 296. 4 billion. Voila. 4 billion. I was using the wrong numbers. This is 4 billion. Right. So approximately IPv4 addresses that we have were 4 billion. With the introduction of IoT, just a minute, here's how many addresses at this point. IoT is nearly limitless addresses. Nah, I cannot find the number 4.3, but I think at some point we definitely have more than, at this point actually, we have more than 4 billion IP addresses, 4.2 billion to be exact. 32 decillion, what's that? What is 32 decillion? 32 decillion IPv6, right? The number of IPv6 we can have, okay, is 2 to the power of 128. That's a lot. That's a huge number. So going back to our lecture, we're just talking numbers. So you can see that we have 4.2 billion IPv4 addresses. But as I was saying, even one, we have more than 4.2 billion. And I think we definitely have more than 4.2 billion cell phones. I think we do have that for more than 4.2. So it means we've already exhausted all the IPv4 addresses that we can have. Right. So due to this, that's why we have IPv6. IPv6 has more addresses, 32 decillion. I'm not sure how many zeros are that, but those numbers, but it's huge. There is no way, we can never say never, but that's a huge number. We cannot deplete that number anytime soon. All right. That's the major problem. Lack of end-to-end connectivity. All right. So when IPv4 started, no problem. We had a lot of addresses, 4.2 billion. When they saw that we are depleting the addresses, they introduced address translation. So address translation, what it basically did, in a network, private network, everyone in this network can use one IP address, public. So inside here, you can have many private addresses, but here they can use just one public. So it means we reserve some IP addresses. How? Because these private IP addresses, they are not unique. I can have another network here with private IP addresses. And when they go to the router, there's a public, one public. And when this one public communicates with this one public, So this one public from here communicates with this one public from here, of which the public IP addresses are unique. So what is only unique are these two addresses. It basically means we have used two addresses instead of many in here plus many in here. That was not. However, the solution came with its problems as well. It ended the direct communication with public addressing. There was no end-to-end connectivity. When you talk of end-to-end connectivity, it means if I'm communicating with A and B, A has an address of .10, B has an address of .9. If I'm communicating with these IP addresses and they do not change, that is end-to-end connectivity. However, if I have a .10 and it gets changed along the way to .11, then it gets to .9. There is no longer end-to-end connectivity there, which is one of the characteristics of IP. So that's a problem as well. However, the solution is IPv6. With IPv6, there is no need for NAT. Why? We have sufficient IPv6 addresses. The last one, increased complexity. NAT was meant as a temporary solution and creates issues on the network as a side effect of manipulating the network headers. Addressing. NAT causes latency and troubleshooting issues. Latency. I cannot stop repeating this. Latency is caused by overhead. A lot of it. So if you want to do NAT, it means you are adding some information to the header. That's more overhead. More overhead, latency. That's a problem. Troubleshooting. If you are troubleshooting, let's say you are troubleshooting a network from this side, from the outside, you want to troubleshoot addresses that are private here. What you see from the outside is address X, which is public. However, addresses that are inside here, it might be Y. So how do you then troubleshoot? It becomes very difficult because when you are looking from outside the network, you are seeing one thing, but what is actually in the network is another thing, because you have private IP addresses here, you have public from the outside. So it becomes very difficult to troubleshoot a network, because to troubleshoot a network, at least you need to identify where the problem is. Identification comes with knowing the IP addresses. If you cannot easily identify what is the IP address, that makes for issues with troubleshooting. With IPv6, we don't have that. Okay, we might have some issues, but not as much as IPv4. Why? No NAT with IPv6. Right, now that we know the troubles of IPv4, that leads us to IPv6, where instead of having 32 bits, we now have 128 bits. Currently, the number of addresses that we can use is 2 to the power of 64. 2 to the power of 64, where the other 64 bits are used as the network ID, the other 64 are used as the host portion, if I can say. 2 to the power of 64, that's a huge number. Improved packet handling. The IPv6 has less fields in the header. Is there no slide where this is explained? Okay. We'll look at this in the next slide. Easy explaining in the next slide. Improved packet handling. What do you mean by that? We'll look at that in the next slide. Eliminates the need for NAT. The need for NAT, we've talked about this one. Since there is a huge amount of addressing, there is no need to use private addressing internally and be mapped to a shared public IP address. So with IPv6, there is no need for network address translation. All right, let's look at the packet header fields. The IPv6 header is simplified, but not smaller. It's not smaller, but it's simplified. Simplified in the sense that it has less fields. All right, for example, we no longer have the flag. We no longer have the fragment offset. We no longer have the header checksum. The reason why we don't have these two is because we don't fragment. With IPv6, there is no fragmenting. You are forced to change the size. The host is forced to change the size of the packet. So if there is no fragmentation, it means we have no need of these two. That explains improved packet handling. It has simplified header with fewer fields. Number two, we no longer have the header checksum. The header checksum is removed. Why? Because at layer number 2, we also have fields which are capable of checking for errors. So the header checksum, its main responsibility is error checking. In IPv6, we don't have it. Why? Because error handling is done at layer number 2. Error checking, error detection is also done at layer number 4. TCP, it deals with that. If a packet is not sent, if a segment, is not sent, that's an error. We don't get the whole message. What does TCP do? Acknowledgement. If an acknowledgement is not sent, it means that segment was not received. Then it gets resent. That explains error checking and error correction as well. So the bulk of the error checking when we're using IPv6 is done by these protocols at layer 4 and at layer 2. So we don't necessarily have to do error checking at layer 3. We call that redundant. No need. That's why we don't have it with IPv6. Right, I can see my time is running up there. Let's have one more. I think we're close to getting done here.